When I was a kid, I loved science, but I felt as though there was no point in becoming a scientist. Everything was already invented. Everything we needed to know had already been discovered, right? I mean, we had equations to describe all kinds of things. Pendulums, rockets, cars, you name it. We were building massive things, flying very heavy planes. The only thing else to achieve was to venture further into space, so I wanted to be an astronaut. Then I realized, okay, maybe there is a point in becoming a scientist. Every day I learned some new phenomenon in physics. Regardless of whether I truly understood it or not, I went to bed with the reassurance that this was all there was, and it governed the world we lived in pretty well. If the math didn't work, it's because I did something wrong. And most of the time, I did. Everything was new and I picked it up pretty fast. But of course, as you grow older, you realize there are more and more things that we still don't know. Bottom line is, we don't know a lot of things. This idea of not knowing, however, takes a whole new meaning with quantum mechanics. But first, let us describe what it means for a theory to work and how science is traditionally done. The scientific method is real. Yes, they actually use it. Scientists observe something. Then they try and hypothesize what might be causing things to happen the way they are. In the case of physics, they try and come up with equations that describe the behavior they're observing. That equation is then tested to see how well the theoretical model replicates reality. The more closely it approximates reality, the better the theory. But notice here that I said approximates. You see, when it comes to physics, theories approximate reality to varying degrees. Some are extremely accurate, others not so much. For example, gases are pretty complicated. They're composed of billions of energetic gas molecules that are constantly colliding and interacting with each other. Because of this, a real gas is extremely hard to determine. So instead, people created the concept of an ideal gas. In short, they're approximations. They bend the rules a bit and get as close as possible to the exact value. No gas is exactly ideal, but the concept of an ideal gas is an extremely useful approximation for most situations. For temperatures near room temperature and pressures near atmospheric pressure, so under normal circumstances, most of the gases we care about are almost perfectly ideal. However, for situations that aren't normal, a bit more work is required. Some rules work really well while on scales that we deal with every day, but once we tweak the settings a bit to different circumstances, our rules begin to break. There's a saying, and it goes, all models are wrong, but some are useful. And honestly, I kind of agree with it. Over the past few million years, humans have been impressively wrong about most things. But it's okay. Models aren't perfect, but some are better than others. In the late 19th century, scientists had another such behavior to model. The sun is bright, like painfully bright. In the sky, it's a glowing white ball of fusion. But, as you know, white isn't just white. It represents a small sliver of radiation called the visible spectrum, and is composed of every color you've ever seen. Now, humans and most things that aren't 5500 degrees Celsius emit light too, but we can't really see it with our own eyes. This is where we enter the infrared and ultraviolet scales. Scientists wanted to know why these colors showed, and if we could predict what colors would emit based on the heat of an object. This sounds like a pretty easy experiment. All objects either emit, absorb, or reflect light, but they wanted an object that didn't reflect anything, something that would absorb all light and only show its radiation, a black body. But like I just said, all objects emit, absorb, or reflect light, so a true black body just doesn't exist in nature. Notice how I said a true black body. For all intents and purposes, the sun, earth, and other stars and planets are considered black bodies. Remember, models aren't perfect. Now, considering that these objects absorb all light, they should have an infinite amount of radiation to reflect, right? Well, when they applied their classical mechanics, the physics that governed the world at the time, the approximation was so poor that in fact the experiment ended up being dubbed as the ultraviolet catastrophe. You can't have an object with an infinite amount of energy like that. It violates the conservation of energy. Classical physics, it seemed, was catastrophically off. Enter Max Planck. Planck determined that the missing link preventing the black body radiation from being modeled correctly was the assumption that energy could be of any amount. Again, if energy could be any amount, then theoretically you could input an infinite value and come back with a solution. To model it correctly, Planck suggested the use of a packet of energy. Instead of continuous energy being sent, It's neatly packaged in set and finite amounts, and thus Planck's constant and the idea of quantization was discovered, a fundamental piece in the foundation of quantum mechanics. For the first time, scientists understood that energy states are discrete and not continuous as previously thought, which is weird. In the quantum world, you play by certain rules that often seem very, very different from what we're used to. It makes all of quantum mechanics a rather unintuitive and confusing subject matter, and while there is merit to that accusation, we must also remember that, much like every other branch of science, quantum mechanics also has its humble beginnings rooted in some very simple ideas. So, what are those simple ideas? And where does that unintuitiveness come from? Well, in my opinion, one of the biggest hurdles in the understanding of quantum mechanics is Heisenberg's uncertainty principle. It is something that we just don't experience in the macroscopic world. It talks about a fundamental, natural limit to which we can measure things. The uncertainty principle states that no matter how accurately or precisely you try to measure something, you can only do it so well. You can never be absolutely certain of a particle's location and momentum at the same time. It comes down to observation, which is strange yet again, because you would think that our measurements should be irrespective of who is looking and who is not. But in the quantum scale, that's no longer the case. Imagine a pool table. There's a cue ball as well as 15 other striped and solid color balls, but let's not focus on the game itself. When you hit the cue ball, it collides with the other balls on the table, making the cue ball then bounce off into another direction until it eventually hits the side of the table. At the quantum level, collisions are happening a bit differently than what you would expect at the macroscopic level. When photons collide, out comes a bunch of different smaller particles that didn't initially go in. Ions, muons, electrons, and other photons. To understand just how weird this is, imagine a car crash. When the cars collide, you'd expect to just see two destroyed cars with car parts flying everywhere. Imagine that once they collide, a table and a basketball come flying out. On impact, there's a complete transformation into something else. It doesn't make sense, obviously. Also, speaking of electrons, they can be in multiple places at the same time, but once measured, a precise location is revealed. It's okay, intuitively this doesn't make sense to me either, but electrons are essentially a cloud around the nucleus of an atom, and only once we measure them does an actual location show its face. When talking about this small scale, our solutions to problems make much more sense as probabilities as opposed to exact values. The actual formula for Heisenberg's uncertainty principle is this. Here too, you see the presence of Planck's constant. The fact that Planck's constant comes up time and time again when calculating things in the quantum realm really reinforces its significance. In a sense, it's self-proving. Because of so many different experiments, we now know the value of Planck's constant with remarkable precision. Now, you may think that you have very little reason to care about the uncertainty principle in day-to-day life, and you'd be kind of right in thinking that. But as we push harder and harder into the frontiers of innovation, even these tiny amounts of uncertainty start to matter. In fact, humanity's most ambitious goals need a level of precision that has never been seen before. The bizarreness of quantum mechanics doesn't stop there. Physicists are now theorizing even more ideas of the multiverse, the idea that multiple universes exist simultaneously, all differentiated by the smallest particles known to man either going this way or that way. That's just one particle. Factor in how many such particles there are and, well, things get too complicated for me to want to explain. The universe, and the events that happen in it, all comes down to probability. We've talked about how quantum mechanics governs the world we live in, but we've really only mentioned the microscopic scale. Does quantum mechanics hold up on the macro scale? Well, it kinda has to. If we use classical mechanics and the values it produces in quantum mechanics, then you should hypothetically be able to take the same quantum mechanics and apply them to larger systems, such as planetary orbits, and still reproduce accurate results. In order for a new theory to take reign, it should be able to explain some phenomena that previous theories explained. In short, it works. This is called Niels Bohr's correspondence principle, and it gives quantum theory even more merit. The more and more we test, and the more examples that prove quantum mechanics agrees with classical mechanics, helps let us know if we're moving in the right direction. But classical mechanics doesn't get everything right. In fact, quantum mechanics changed the way we view light itself. Something we encounter every day we wake up is something that we're still figuring out even today. Wave-particle duality is a concept that changed the fundamentals of nature forever. Through the work of Max Planck, Niels Bohr, Albert Einstein, and a handful of other quantum physicists, it was discovered that light not only functions as a wave in the spectrum, but also functions as a particle, at the same time. Their existence is intertwined. Einstein proposed that light functions as a particle, photons, a quanta of light deduced from Planck's theories, and it works. Einstein was an amazing physicist, but few people know that he actually won his Nobel Prize for the photoelectric effect for his involvement in quantum mechanics. It seems as though we must use one theory and sometimes the other, while at times we may use either. We are faced with a new kind of difficulty. We have two contradictory pictures of reality. Separately, neither of them fully explains the phenomena of light, but together, they do. Albert Einstein said that, and he explained it better than I ever could. Two different pictures of reality, two different theories and views of the world come together to explain it all. It's astonishing to think how one constant could reshape the way we see reality forever. We don't know why it's this way, except for the fact that nature intended it to be this way. Constants are seen throughout nature: Planck's constant, the golden ratio, pi. The list goes on. As with most definitions in physics, they seem to be used in a very specific manner. Velocity means something very specific. Amplitude means something very specific. The word uncertainty too means something very specific. But it's hard not to feel that this word, uncertainty, hits home differently these days. It is perhaps the most single apt description of the past few months for the entire world. While I don't expect everyone to be as fascinated with the uncertainty principle as myself and most physicists are, I do hope that you can take just one thing away from it. There's always going to be uncertainty in life. Despite our best efforts, there's only so much we can control, and while it can seem limiting, it can also be the cause for hope and excitement. Uncertainty is, after all, a two-way street. Even genetic exactness cannot rule out uncertainty. Genetics are extremely powerful, but there's even a limit to that power. Identical twins can not only have the same exact genes, but can also share the same environment since the day they're born. And yet, they will still grow up to have different brains and become different people. The detailed structure of the brain is partly shaped by genes and environment, but the rest is relatively random. And I use random for the lack of a better word. Nothing is completely understood, our bodies included. What we see now as random could be seen as obvious in 100 years' time. History, as always, is a good example of this. The quantum world is full of random collisions. But oddly enough, all this randomness brings the order that we observe in the world. Science isn't constant by any means, but it is constantly improving. I wish I could say the same for everything else.